Okay, thank you very much. Thanks to the organizers for having me. Let's see, there is a pointer somewhere here. I have very fond memories of Lumini. I was here first time in 2004 as a postdoc with Thomas, and I was preparing to meet Genna for the first time. We came a bit early. We came on Saturday, I think, and did some sightseeing in the city. Me and Philip Lindskog and Thomas, and we were discussing a new problem that Genna has posed, I think, or Genna and Thomas discussed about Ruin probabilities with regularly varying claim sizes, and I think we discussed this problem during our sightseeing and eventually ended up on a bench in the harbor solving the essential parts of the problem. So that was my first memory of Lumini. And I've been back here a few times since, and I really love this place. Today I will talk about some joint work with a former student of mine, Martina Favero. She finished her PhD a bit over a year ago, and now she's a postdoc in Warwick. And this started off as a problem not at all related to this conference. It was a problem on importance sampling. I had done some work on efficient importance sampling, and I came across some papers from around late 90s, early 2000s about importance sampling in population genetics. And I was thinking that maybe the tools I know for studying efficient importance sampling can be used in that context. And so I posed this problem to her, and it turned out to be much more difficult than we anticipated. And along the route came out these power laws that I had not seen before, and that are perhaps of different type than what we usually see or what we have seen during the talks today. But I think they are interesting, and there are several connections to the theory of regular variation. So I'd like to present this to you, and I'll just try to highlight what is sort of the relations to regular variation in this talk. So the Kingman coalescent, I will describe what it is because probably not everybody is familiar. It's a standard model in population genetics, modeling the ancestry of a sample. What we will consider is the sampling probability. So this is basically you take a sample from a population and you look at the specific loci and the allele at this loci, and what's the probability to see a certain configuration. And as the sample increases, you will see a power law of the sampling probability. You can also study this ancestral history a bit more detail, and then you can start to count the number of mutations in the ancestral history of your sample. And if you do that, you will come to a limit, which is a limiting Poisson process, which has an intensity that explodes like a power law at the origin. So that is what we will see. And we will also study some weak convergence of this Kingman coalescent as the sample size increases. And then there are also several construction very similar to hidden regular variation appearing. So basically we have a certain rate in the interior of the state space and different rate on the axis. So in hidden regular variation, it hasn't come up today, but most of you are familiar. There you have a regular variation that you have asymptotic dependence, so the spectral measure will be concentrated on the axis. And if you remove the axis, you can have a second irregular variation in the interior. And so it's something similar happens here. There's one behavior on the axis that we sort of try to avoid, and so we need to exclude that part of the state space and look at the convergence in the interior of the domain. So those are the sort of main highlights related to power laws and regular variation that you will see. Okay, so I will start with a bit of a background on basic model of population genetics. So, and this is just a way to motivate the Kingman coalescent. The Kingman coalescent appears in quite general settings nowadays. I will stay with a very simple one where you only have birth and mutation in the model. You can have other genetic forces like selection and recombination and so on, but I will not go into the more refined population genetic models. In this picture, it runs from left to right, so time runs from left to right. And it works in, this is the right Fisher model with mutations. So this is one of the basic starting models. And you have a population of n individuals, capital N, and capital N is being fixed throughout the time. And you model the evolution of allele types. So think of a specific loci in your DNA. You can have, say, A, C, T, or G in this loci. And you see how the type at this particular loci evolves through the generations. Okay, so here in this model we only have two types. So these guys, these individuals have the yellow type, and these guys have the blue type. And then it works as follows. It's not very sharp. I think the picture, maybe it's better for you. There are some lines going between the dots here. Maybe can you see them? No? Yeah. Yeah, I'll try to draw a picture. It's maybe good for reference. Okay, so so I will draw a time going down, and then we have a fixed population size, and say we have two types. We have the so there are n individuals, time is going this way, and in the next generation you select your parent uniformly at random. Okay, so this individual will select maybe this parent, this individual maybe selects the same parent, this one maybe selects this one maybe this one, and this one maybe this one. And then types are inherited from the parent to the children. So this will be filled in, and this has to choose a parent, maybe also this one. And then it continues like this, but sometimes with some probability gamma that can depend on the type, so that's the gamma I here, there is a mutation. So maybe this guy selected this parent, but there was a mutation happening here, so it changed the type. Right? And so it goes on like this. And yeah, this is what you see in this picture, and the red dots are the occurrence of the mutations. And then you have some final configuration at the end. And then what you can do, and what is often done, is that you send the size of the population to infinity, and you study the frequency of the types in the model. Right? So if we let X capital N be the frequency of the allele types, and we study it after number of generations that also scale with the population size, then you will have a weak convergence of the frequency of allele types, and it will converge to a diffusion process called the Wright-Fisher diffusion. Right? And you can, this is an illustration with more types, maybe 5 types. And so you should read the frequency is basically the width of the color for that particular type. And so the Wright-Fisher diffusion is going to describe how the frequency of the allele types evolve for large populations over long time horizons. And there is a drift that basically expresses, it has the theta, which is mutation intensity, and it has these gammas that were the mutation probabilities. There is a pi, there's a matrix P, which is going to be important. It's the, I didn't say it here, it's the transition probability or the mutation probability matrix. So given that there is a mutation, what's the probability it goes from I to J? Okay, so this is the Wright-Fisher diffusion. And then we come to the coalescent. So the coalescent takes the following point of view, that we go back to the Wright-Fisher model. And then at some point in time, let's write it as the last observation time here, we take a sample of little n individuals, right? And we observe their types. And that's the only thing we see. We see the types of these n individuals at the bottom. And then we want to know something about the evolution of this population, like the mutation intensity. So how can we say something about the mutation intensity only observing these 3 individuals down here? Well, we try to do some maximum likelihood. What is the probability of seeing precisely this configuration of these 3? And then we can do some maximum likelihood or something like that. Okay, and then comes the coalescent as sort of a help to do this. So what you do then is you look at these 3 selected individuals and you create their ancestral history. And you do it all the way back until you see a common ancestor. So this is called the most recent common ancestor. And then you can keep track of a sort of simplified picture of the ancestral history. This line corresponds to this individual, this line to this lineage, and the blue to this one. And you just look at what is the next point in time when something happened. Well, it's this time where these 2 lineages coalesced into one. Okay, so you denote this. And then you had a mutation event on the second lineage. You denote that. And then you follow it back to the most recent common ancestor. So this is, so this is the sort of the coalescent picture of the Wright-Fisher model. And when you send capital N to infinity, you could see a weak convergence of this coalescent model, and that's the Kingman coalescent. So you only keep track of this essential information when something happened and not what happened exactly in each generation. Okay, so we will consider this. I will describe it more mathematically in a little bit. We will consider this with a fixed number, d types. So that will be just some finite number, think of 4. We will have a sample size, which is the size of the sample at the last generation. And this will tend to be large. We will have a model that admits coalescence and mutation. This model appears, as I mentioned, as the limit in the Wright-Fisher model, but also in other basic models of population genetics, like the Moran models. And it's used very much to do inference, which I will also come back to, but basically to calculate the likelihood of an observed sample. Okay, so what we will do now is that we will consider the jump chain of the coalescent. So that is basically just a Markov chain on with a state space that counts the number of types in each, between each event of the coalescent model. So we denote it by hk, so it's d-dimensional and just integer valued. It will count the number of individuals k steps into the ancestral history, k events into the ancestral history. And we may consider this jump chain either sort of in the evolutionary time direction, sort of starting from the somewhere way in the past at the most recent common ancestor and evolving forward. So this will basically be this picture here. You start here where there is one individual of one type, and then it's splitting into two individuals of the same type. Here it's splitting into one is mutating, so it's transferring to one individual of type 1 and two individuals of type 2, etc. Or we can consider it sort of backwards in time when you start from the observed sample and reconstruct the ancestral history backwards until the most recent common ancestor. And the simple way to look at it is forward in time. And then you have explicit transition probabilities of this block counting process. So the events, if you're starting, if you're now at a configuration n, so this is a d-dimensional vector of integers with a number of different types, there can be two things happening. There can be a split. So say that the j's, in the j's type there is a split. So this means you will add one more individual to the j's type, and this will happen with a certain probability. Or there can be a mutation from the i's type to the j's type, which means you will decrease in the i's type and add one in the j's type, and this will happen with this probability. Okay, so it's a very simple Markov chain as you view it moving forwards in time. But what you would like then, if you want to do inference, is to look at the marginal probability of this Markov chain at the sort of point of observation. And this means we would like to calculate the likelihood, which is we call the sampling probability. So this is the probability to see precisely the configuration that I have observed. So one way to look at this is that you look at the whole process, and then you treat the whole ancestral history as an unobserved. And so you marginalize out the whole ancestral history. Another way to look at this is from the point of view of the Wright-Fisher diffusion. And if you recall the Wright-Fisher diffusion, it tells you the allele frequencies of the population. And so if you sample at some point in time, you can imagine the Wright-Fisher diffusion being run from somewhere minus infinity. It has been run to stationarity. At this time, I will sort of sample the allele frequencies, and then I will take a multinomial sample with those probabilities. Okay, so this is nothing but a multinomial sample, multinomial probability with xi as the sampling probabilities, where xi is drawn from the stationary distribution of the Wright-Fisher diffusion. So this is an alternative way of representing the sampling probability, and it's sort of difficult to compute. Either you need to do this marginalization with the full ancestral history, or you need to calculate this, which is not very explicit. So what is typically done is doing this with Monte Carlo by marginalizing out the ancestral history. So then what you do is you do the following. You try to compute the sampling probability by starting from the observed sample and reconstructing ancestral histories using some sampling distribution. So we are starting from observed configuration, let's call it H0, and then we're sampling the ancestral history backwards in time according to some selected sampling transition Q. And then we can compute the sampling probability by averaging out, then you get the likelihood ratio between the forward probabilities that are explicit and the sampling backward probabilities. You will get this likelihood ratio up until the tau is the time you reach the most recent common ancestor. And so this is what you do. You calculate this, and then the question is how to select the sampling transition Q. And there are some good suggestions for doing this. And two main ones that I will just briefly tell you about is the problem is that, of course, if you could use the true backward sampling, you would like to do it, then you wouldn't have a problem because everything would be explicitly known. So this is like knowing the conditional distribution or knowing the zero variance change of measure if you do importance sampling. So you could write the backward, you can write it in terms of the forward just with base rule, and then the marginal is the thing we're trying to compute. And then the Griffiths-Tavares algorithm is basically based on sampling proportional to the forward probabilities. So you're standing at HK, at this configuration. You can calculate the probability to go from some other configuration to this configuration forward in time, in evolutionary time, so in this direction. And so let's do that and just normalize it to be a probability. So that's one suggestion. An alternative suggestion is to just rewrite the backward probabilities in a particular way with this pi distribution, which is really expressed in terms of ratios of the sampling distributions here. And then come with a suggestion for instead of pi, you use some other distribution. And this is proposed by Stevens and Donnelly in 2000, and this is probably the most used today. And there are a lot of good heuristics for why you should choose this, but there hasn't been any sort of rigorous results about the efficiency of these type of algorithms. And that's why I was kind of intrigued by this to see, can we say something about the efficiency of these algorithms using the theory of efficient importance sampling. Okay, so that was, and what do we mean by efficient importance sampling? Well, from a general perspective, if we're trying to compute some expectation using importance sampling, we sample xn from some new distribution qn, and we take the sample average of independent copies. And then if we are in a setting where this sort of goes to 0 as n goes to infinity, which would be like a rare event probability or something like that, to have some efficiency, we would like the sample variance to decay like the quantity squared. So if we're estimating a small probability like this, we like the standard deviation to be roughly of the same size as the probability we're estimating. And one way to do this, if you have exponential decay of probabilities, is to say that the exponential rate of decay of the variance, which can be written like this, is the same as the 2 times the exponential decay of the probability. And this is often used in light-tailed settings where you have sort of large deviation principle with exponential decay. In a heavy-tailed setting, you often look for algorithms with bounded relative error, which is stronger, meaning that the second moment of your estimator divided by the probability squared, say, is bounded. So these would be things that one would look for, and nothing of this type has been done for this important sampling algorithms in population genetics. But they are used a lot, and they are in most of the standard software for doing inference in the population genetics context. Okay, so that was a long introduction. Now let me try to come to the results. So I will consider this from the point of view of a large sample size. So let me first say a few things about that setting. So it's convenient to have an asymptotic setting when we talk about efficiency or asymptotic efficiency for important sampling algorithms. And the setting of large N is, I think, quite useful. The problem with this, with computing the sampling probability really is present when N is larger than, say, 40. So there is a recursion formula that one can use that explicitly evaluate the probabilities, but this is only feasible to implement for quite small sample sizes. And the genetic samples today are increasingly large, in the tens and hundreds of thousands, and perhaps in that range you can also question the sort of validity of the Kingman coalescent. So there is, I think, from the point of view of important sampling algorithm, it's quite sensible to look at the large N limit, but there are some questions about the validity of the Kingman coalescent when sample size is very large. So recall the Kingman coalescent appears as a limit model itself when the population size is large. So somehow the population size has to be significantly larger than the sample size for this to be a good limit. And that may not always be the case if sample size is very large. Anyway, let's look at this. I will just quickly recall the expression for the backward sampling probabilities, and I will show you a typical path if you start to simulate if you simulate the process from its most recent common ancestor to a particular point, and then let me reconstruct it sort of backwards. So we have this, going to look at this scaled sample path on the block counting process of the Kingman coalescent. So we're going to start it at some point here, where typically the components sum up to 1. So we have normalized it in that way. And then when you see a vertical jump, it corresponds to a coalescent event. So it means that one of the types, in one of the types it was a coalescent event, so it reduced. And when you see a diagonal jump, it means it was a mutation event. So if you put it in this, now we just have two types, so that's why it's two coordinates. So what will happen with this process is that as you increase n, it's going to become closer and closer to this straight blue line. So it's not, from the simulations, it doesn't look to be a very interesting limit process. It's, and that's what the result will show. It's just converging to this straight line here. But there's more to the story, so I will try to say something about it. I don't need to talk about regular variation, I think. So what is there in this story? So the first part is to look at the sampling probabilities and the determinate asymptotic behavior of that. And I hinted briefly this will lead to a power law. When we have that, we can also look at the asymptotic behavior of the transition probabilities of this block counting chain. So the first will basically lead to the second. And then we can look at the weak convergence of the jump chain. So that's basically this picture here. This will converge to a straight line. And also the number of mutations in the ancestral history. And here will be a Poisson limit. And then in addition to this, we can also add the cost component so that there is an associated cost with each transition. And this is needed in the study of performance of importance sampling algorithms. Okay, so let me come to the first result. So this is the sampling probabilities. And so here I will use the representation as a multinomial sample with the probabilities coming from the stationary distribution of the Wright-Fisher diffusion. So if the mutation probability matrix is irreducible, then there is nice and smooth stationary density of the Wright-Fisher diffusion. So let's call it P tilde. We don't know much about it other than that it's smooth. Then we look at the sampling probability at some sort of normalized points. So I will normalize it in such a way that yn sits in the lattice with the endpoints and it converges to some point in RD. And so if I scale the, if I look at the sequence of sampling probabilities, it's going to decay like a power, an exact power with the coefficient 1 minus d. D is the number of types. And the limit, it will have the norm of y, the normalized configuration, and it will have the stationary density. Right, so the important part here is the rate of decay, which is this power law. I will say a few things about the proof in a little bit, but I will just start stating this result, and then I will show you a bit how it's done. Once you have this result, one can look at backward transition probabilities. So say we are standing at the configuration n times y, so I now normalized my configurations. And so then what is the likelihood that you will take a step in the direction of minus v? So v will either be corresponding to a coalescent event or a mutation event. And then this probability will converge just to the normalized the frequency of the type J if it's a coalescent, and it will decay much faster. It will decay like 1 over n, the mutation probability, and there is a limiting quantity here that we can express in terms of the mutation matrix and the current configuration of the normalized configuration of the process. So this means that when you have many individuals, sort of large sample size, the likelihood of seeing a mutation is very small. It's like 1 over n, whereas it's order 1 to see a coalescent event. Right? And that sort of explains why, here it's normalized with n. So in the most part here, you have at least, if you're above epsilon here around the origin, you have order n in number of individuals. So you will basically not see many mutations there. So that would explain, and the coalescent rate goes sort of just to the frequency, which is the slope of this line. So that sort of explains the behavior we see in the simulation. All right. So what if we now look at the joint process, a bit more interesting. So let yn be the normalized jump chain, and let mn denote the number of mutations in my sample from I to j. So this will be a matrix valued process. I keep track of all the number of mutations between two types. And then what happens is that intuitively this normalized block counting process will approach a straight line, and it's just from the starting point pointing straight towards the origin, and you will hit the origin in this normalized time scale, which is precisely at the time norm of the starting point. So that's not so interesting. What is more interesting is this number of mutations. So it will approach a matrix of independent, inhomogeneous Poisson processes, and the intensity of these processes will be precisely what comes out of the limit here. If you just replace y with the configuration at time t, so that's this deterministic process at time t. And so what you see happens here is that when y approaches 0, which is infinite time at this time norm of y naught, the intensity is going to explode like 1 over y. Right, so you will have this, and if you look at the integral of this, it's going to have a logarithmic explosion at the origin. So we will see this limiting inhomogeneous Poisson process exploding at the origin. And so this causes some problems. I will come back to this in a little bit, but these are sort of the main results, and I will tell you how we go about to prove them in a little bit. Okay, any questions so far on the formulation of the results? Did I lose you? All of you? Yeah, I did. Okay, so let me try to catch you again. So what is going on here? So we have this, let me write the normalized sampling probability. So it's just this normalization constant or factor, and then it's this multinomial sample from the stationary distribution of the Wright-Fisher diffusion. So if we just write this out in terms of the stationary density, which we call p tilde, is just this integral with respect to the stationary density. And so now, taking the limit as n goes to infinity, it looks like a simple bounded convergence theorem or something like that. And it's not quite so simple, because what happens is that the integrand here will approach Dirac function. So it's going to explode at a certain point and be very concentrated. So there's no like bounded convergence theorem that we can use. But what is convenient is that you, from this x to the ni here, we sort of identify something that looks like a Dirichlet density. Okay, so we can interpret this as being some factors, this multinomial factors, a beta function, and then the expectation of the stationary distribution of the Bright-Fisher diffusion evaluated at a Dirichlet distributed random variable. And the Dirichlet random variable has parameters that depend on n. And so then what you need to do is to do a local limit theorem for Dirichlet densities. So basically, we have a central limit theorem telling us that if the there will be a Gaussian density, the Dirichlet will converge weakly to a Gaussian distribution if the parameters of the Dirichlet goes to infinity. And we need a bit more refined, we need the local limit theorem for the corresponding densities. So that's what is involved here. And basically, the power law does not come from the Dirichlet part. Right? So the power law actually comes from just this combinatorial thing. So the Dirichlet part is basically just a technical tool, but the power law comes from the prefactor here. And so what is the explanation? I don't really have a great explanation for why there should be a power law coming up here. I mean, it comes from the calculation, you could say. But the main reason that I think is somewhat true is that this probability distribution here, it's probability distribution on the simplex of size n. So meaning it's a simplex in the dimension where the sum of the variables is equal to n. Okay. So if you take the uniform distribution on the simplex, it's just 1 over the number of elements. And then what is the number of elements in the simplex? Well, it grows like n to the d minus 1. So it's basically the size of the state space that has this power behavior. And I would say that's sort of the reason for this d minus 1 appearing here. But then I have tried to do some to use this to prove a result like this, say that the density is absolutely continuous with respect to the uniform density on the simplex, and there is some bound, but that hasn't worked out. But still, I think that's sort of the reason for this power law. Okay, then if you go to the transition probabilities, then you can write out the backward transition probabilities with this pi. Here I wrote out the pi. It's expressed in terms of the sampling probabilities. So now when we have the asymptotic for the sampling probabilities, you can basically plug this in and you will get the result for the transition probabilities. So that's basically a simple consequence. Then if we move to the process setting, we have this picture now with we start from some normalized configuration here, why not? And we study this process, which is the normalized block counting process. And for this, we use a generator approach. So it's, I found this the most convenient, and that's really the way we got the limit result, is by looking at the generator of this Markov chain moving sort of back in the ancestral history. So if I don't think I have time to write this out, but you do this simple calculation, and you keep, you express the generator in terms of these backward transition probabilities, rho n for coalescent and for mutation. And then you just go to the limit of the generator, and you see that you will get some limiting generator. And this is then the candidate as a generator for the limiting process. And then what happens is that you can do this first in a somewhat simpler setting, which is the parent-independent mutation setting. So this is the case where the mutation matrix does not depend on the parent. This simplifies things a lot. In fact, it simplifies so much that everything that I am talking about can be made explicit. So you can calculate the sampling probability exactly, you can calculate these transition probabilities backward exactly. So everything can be done with exact calculations in this case. Right. But if you do it anyway, you will see that the generator, you will have this limiting generator corresponding to the deterministic part and this Poisson process. And a problem then is that the mutations explode at the origin. It may not be such a big problem. It's a homogeneous Poisson process. It explodes at the origin. Let's just remove the origin from the space. We can replace it with the cemetery point that it will reach in finite time. And that sort of works. But the problem is to extend it to the parent-dependent setting. So the way to extend the results to the parent-dependent setting is to do a change of measure. And in the change of measure, when you go from parent-independent to parent-dependent mutations, is that there is a contribution every time there is a mutation in your ancestral history. So the likelihood ratio is going to depend on the number of mutations between all the different types. And to then extend the convergence, you need the convergence of the generators, and then there is a problem on the axis. So the result we have for the asymptotic of the transition probabilities, it only holds in the interior. And in fact, on the axis, there's a different behavior. On the other hand, you don't really think you need the axis, because the process is essentially going to follow a straight line to the origin, so it should never hit the axis. So the way to solve this is basically to remove the axis from the state space. You redefine your convergence just like you do with hidden regular variation. So you have a new metric that where sets that are bounded away from the axis are relatively compact in this new space, and then you work with the convergence on this modified space. Okay, so that's what you need to do. So there are quite a lot of technical steps involved here, but finally we get this limiting result that also in the parent-dependent setting we have this independent sequence of inhomogeneous Poisson processes in the limit, and we have the straight line for the normalized block counting chain. Okay, so the last minutes or so, I thought I'd say a few words about the extensions to importance sampling. So everything that I told you so far has been written down, so the transition probabilities and the sampling probability, they are published. I'll show you the reference in a while. And this weak convergence is submitted a few weeks ago. And the importance sampling part is still ongoing, and I'll tell you a little bit about this in the last few minutes. So what you can do is you can, in addition to the jump chain and the number of mutations, we can have like a cost process that associates a cost with each transition of the block counting chain. So it's a multiplicative cost. There is some initial cost that is, say, 1. And then as you go each generation back in the ancestral history, if there is a coalescent event, there is a certain cost that may depend on the state at that point in time. And if there is a mutation event, there is a different cost that may depend on what type of event it is and the current state. So why do we introduce this cost? Well, the cost will come up naturally as the likelihood ratio when we do importance sampling. So that's really the motivation for this cost. But now we can think of it as just something general. And then if you have this, there is a natural limiting cost process. So as n tends to infinity, you can sort of think of this, you can think of these products being exponential to the sum of the logs, right? And if you do that, you can sort of expect the sum of the logs is going to be, the sum will be an integral, and the logs will sort of see in this, the limiting cost is sort of related to this a. There is some continuous cost in the limit, and it relates to this deterministic, you integrate against this deterministic y process, which is the limiting process for the y. And there is a separate cost for the mutation part. So each time there's a mutation, you sort of add up the logarithmic cost for the mutation transition. And what you need here is that, so to get this limiting cost process, you need the following assumptions on the cost. So the cost for the coalescent events is close to 1. And it's so close to 1 that it deviates from 1 at rate 1 over n. Right? And a is then the sort of limit of the cost away from 1, or the expansion of the cost at the 1 over n term. Whereas for the mutation events, you have a limiting cost, let's call it bij. There shouldn't be an n on the b term here. But here you need that the b is greater than or equal to 1. So basically what you will have is that you need the b's to be greater than or equal to 1, because otherwise you could have this oscillating product of plus things that are slightly bigger than 1 and slightly smaller than 1, and you will never get something from there. So these are the sort of basic assumptions, and under these assumptions you will have a limiting cost process that you can express like this. And so if we turn to the importance sampling, the way to look at this is we look at the normalized importance sampling weights. And so what are these normalized importance sampling weights? Well, I will take the likelihood ratio between my sampling, backward sampling transitions we saw in the beginning and the forward probabilities. And I will normalize with the sampling probability that I'm trying to compute. So this is sort of the normalized thing. I can write this out, and then I will just get this product where I have the sampling, my selected sampling probabilities, sampling transitions in the denominator, and the forward probabilities that are explicit in the numerator. And the ideal thing would be that the likelihood normalized importance sampling weights are equal to 1, which would correspond to taking, and now I've written them as both the backward in the numerator and the denominator. If I could take Q as the true backward probabilities. And if you relate to sort of these notions of efficiency, what you would do is you would study the normalized second moment, or the second moment of the estimator. It will have the probability. You can do it like this. You write the probability squared, and then you have the expectation under the original measure of the normalized likelihood ratio. So you could study what we really need is the expectation of this normalized importance sampling weights. And what we can say basically is that now you can write out these normalized importance sampling weights in terms of a cost process. Right? So you will have if you're sampling like in the Stevens-Donnelly algorithm with suggested pi hat, the cost when there is a coalescent will be the ratio of the suggested pi hat with the true pi hat, and it will be a similar ratio of the pi's when it's the cost for the mutation events. And so you can identify these costs, and then you just need to check the conditions on the previous page to see that we actually have weak convergence of this normalized weights. And if we have weak convergence, we just need some uniform integrability to have convergence of the expectation of the normalized weights, which will give us some bounded relative error. Problem is, the story basically ends here. So what I can do, for the Stevens-Donnelly algorithm and the Griffiths-Tavares, I can show that the pi hat has the desired, so the proposed probabilities have the desired behavior, but in order to analyze pi, I need some more refined estimates. So if you recall, the results I had for pi was that pi tends to the, I have an asymptotic result that say that pi tends to the frequency, which is yj divided by norm of y. But I need something more refined here. So I need to be able to say something like this. And so if we do the same, but we replace cj minus 1 with pi and aj with just a frequency, I need to say not only that pi converges to yj, but I need to say it converges at rate 1 over n. Right? And so far, I don't know how to do that. So this is the current state of the work. And I will finish there. There are 2 papers that are completed with Martina, and then the third on the importance sampling. We hope to be able to work this out, the last issue, but otherwise, whenever that is done, it will be up on archive. So thank you very much for attention.